Hello friends, today we are going to see Onsager Equation, validity and verification. I am Dr. Gerald Anthony, Assistant Professor in Chemistry, St. Xavier's College, Palayankotte. So in Onsager Equation, consider a simple chemical reaction. Here the reactant A is converted into product B. Here in the forward reaction the rate constant will be K1 and in the backward reaction the rate constant is K minus 1. So we are writing the rate of the reaction on the basis of the rate of disintegration of concentration of A. So here in forward reaction there is a disintegration of concentration of A. So we are writing the value as K1 into concentration of A. So in chemical kinetics you will be writing the concentration in square bracket. Here we are writing it as Ca. That is concentration of A. And also in backward reaction there is a formation of A. So we are discussing the rate with respect to disintegration of concentration of A. So now what we are doing, now we will be subtracting that value minus K minus 1 Cb. So now the rate of disintegration of A, so the A will be disintegrated automatically to B. So this value can be also used for rate of formation of B. So the same value can be written like this. So dCb by dt is equal to K1Ca minus K minus 1 Cb. Now, so at equilibrium, the rate J will be equal to, so the rate of disintegration of A will be equal to rate of formation of B. So both that values will be equal to 0. So you can see at that condition this equation 1b or 1a, any equation, both the equations are same, so this equation will become 0. So as soon as this equation becomes 0, now what happens, k minus 1 cbe will be equal to k1 cae. So now what we are doing, so now we are rearranging the k and c values at one side, so we will be getting the values as such, k1 by k minus 1 is equal to c by cbe divided by cae, that is concentration of B at equilibrium divided by concentration of A at equilibrium. Since we are discussing about equilibrium rate, so you have to use the superscript as E on both the concentration term, and then we have to equate it. So when we are equating in such a way, so what happens, so you have to write the same equation at equilibrium state as K1 CAE minus K minus 1 CBE, then it is equal to 0. So we are equating it. So now you are equating this equation, you will be getting such a value. So this value can be considered as equal to another one rate constant K, capital K, total rate constant capital K. Okay, so now we are going to see we are going to introduce a new term, alpha. Alpha is the difference between given concentration and equilibrium concentration. So the given concentration is given as, so it is represented as concentration A, Ca. So equilibrium concentration will be Cae. So the difference between the initial concentration and the equilibrium concentration is the alpha A. So alpha B will be also in same way, difference between the concentration B and equilibrium concentration CBE. So what happens at equilibrium, we are assuming that at equilibrium A, so we know the reaction A is converted into B, some x moles of A is converted into B. at equilibrium. So obviously there will be a loss of X moles. So concentration of A can be written as Ca minus X. And also there is a gain of X moles by B. So we can write the concentration of B as Cb plus X. Both are taking place in the equilibrium condition. So the Ca minus X will be equal to Cae, Cb plus X will be equal to Cbe. So now here we are adding the Ca and Cb. So here we can see this is Ca. So Ca is equal to Cae plus X. In same way Cb will be equal to, so when we bring this X to opposite side it will be minus X. So when you adding the Ca and Cb, so here what happens, Ca is equal to Cae plus X. Cb is equal to Cbe minus X. So we are adding Ca plus Cb, X get cancelled. So we will be getting the equation, third equation. So now from equation 2, so we can also find the alpha A plus alpha B. So we are getting alpha A value here, alpha B value here. When you add these two value, you will be getting a such equation. This is equation number 4. And also we know that the rate of the reaction J is equal to, so already we have seen that the rate of the reaction will be equal to J is equal to K1 C C sorry Ca, so which we have mentioned in the first equation, minus K minus 1 Cb. Okay, so since here we are using the term instead of Ca we can use the term Cae plus alpha, so we can derive this new term from equation 2. So you can see I will rub all the other thing. So we can see J is equal to K1 Ca minus K minus 1 Cb. So Ca value can be obtained from this equation too. Ca is equal to alpha A plus Ca. If you bring this minus Cae opposite side, it will become plus. In same way Cb is equal to, if you bring the Cbe opposite side, it will become plus Cbe. So here now what happens, we are instead of Ca we are substituting Cae plus alpha A. So Ca is equal to Cae plus alpha A. Cb is equal to Cbe plus alpha, based on the equation number 2. So we will be getting the equation as such. So now you can see. So we already know that K1 Ca is equal to K minus K minus 1 Cbe at equilibrium. So the rate of the forward reaction will be equal to the rate of backward reaction, and also we can see that the amount of A which is remaining will be converted, it will be usually equal to minus of the amount of B remaining. Okay, so the equilibrium concentration of A will be it will be alpha A will be the equal to minus alpha B. So we can see that we can substitute all these terms. So as soon as when you are substituting this term, you will be getting the equation 5. So we may know that already in the previous equation, J is equal to K1 alpha A minus k minus 1 alpha b. This is the equation. So you can see k instead of alpha b, so we are using the term minus alpha a, because alpha a is equal to minus alpha b, or we can assume it as alpha b is equal to minus alpha a. So when you substitute this value, so you will be getting the value like this: J is equal to K1 alpha A. Instead of alpha B, we are substituting again minus alpha A. Already there is a minus, so minus into minus plus, plus K minus 1 alpha A. So in both the equation, alpha A is in common, so we can remove this alpha A, which is done here. So alpha A is removed, the equation will be alpha A is taken as common, so alpha A into K1 plus K minus 1. So now we know that affinity of a reaction is equal to chemical potential of A minus chemical potential of B. So already we know that the rate of the chemical reaction J is directly proportional to A affinity of the reaction. It is equal to a proportionality constant. Using proportionality constant L, we can make it equal. So J is equal to LA. So instead of A, we can substitute the term nu A minus nu B. So we already know that nu is equal to nu naught plus RT ln C. Here the C means concentration. So already we know there are two concentration terms, Ca and Cb. So we have already found the value. Ca is equal to Cae plus alpha A. Cb is equal to Cbe plus alpha B. So already we have found that equation. We can use that equation here, and you can write nu A and nu B individually. So you can write the chemical potential for A and B individually. So here you can see the here in we are taking CAE in common. So automatically now what happens if you take the CAE is common, so this factor will become 1, and here you can divide the alpha A by CAE. If you multiply the CAE with inside the bracket, you will be getting the actual formula in the previous slide, that is Ca is equal to CAE plus alpha A. In same way here also, if you multiply the CBE, you will get the actual formula in the previous slide, that is CB is equal to CBE plus alpha B. So now we are writing the formula nu is equal to nu naught plus RT ln C. So here for concentration of A, so you know the formula nu is equal to nu naught plus RT ln C. So for A you can write nu naught A RT ln CA. So you have the CA value here. So we are substituting that CA value. So whenever you are substituting that CA value, so you can see nu A is equal to nu A naught plus RT ln, instead of CA you can write this term CAE into, sorry, you can write it this way. So nu A is equal to nu A naught plus RT ln, instead of CA you are writing this term CAE into 1 plus alpha A divided by CAE. So usually the value will be nu A is equal to nu A naught plus RT, right? Nu A is equal to nu A naught plus RT ln CA. So instead of CA we are substituting this term. Here you can see, so there is a multiplication value. So in ln the multiplication value can be written in the plus form. So only, so we are splitting the CAE into 1 plus alpha A CAE as RT ln CAE plus RT ln 1 plus alpha A CAE. In similarly you can write for nu B also. So when you are writing for nu B, you will be getting the value as such which is given in this slide. So chemical potential have been found for A and B. So now we know what is A. A is equal to nu A minus nu B. So we have already got nu A and nu B value. So we are subtracting this equation by subtracting both the values. So here this is that equation. This can be written in such a way. So you please note down this equation. Now we are moving to another slide. Next slide, equation 7. So here you can see that is at equilibrium nu A naught is equal to nu B naught, and concentration of A at equilibrium is equal to concentration of B. So totally all the values will get cancelled. Only these values will be remaining in this affinity. Okay, affinity term A. So if you go through the previous slide, if you substitute all these values, if you substitute according to this assumption, all the terms will cancel. Only this RT ln 1 plus alpha A by CAE minus RT ln 1 plus alpha B by CBE will be remaining. So here also we are having RT in common. You can take the RT as common. Now we know that alpha A by CAE and alpha B by CB is very much less than 1. So instead of writing this ln 1 plus alpha A by CAE, we can simply write the term alpha A CAE. In the same way, instead of writing ln 1 plus alpha B by CBE, already this is 1 plus alpha B by CBE will be a very small value, very much lesser than 1. So we can write it as such as alpha B CBE. Here also alpha A CAE. So if we substitute in this way, you will be getting an equation as such, alpha A by C. So ln will be removed, 1 will be removed. Here also ln will be removed, 1 will be removed in equation 8. So a new equation is, a modified equation is obtained as below, which is encircled here. So now we already know alpha A is equal to minus alpha B, or alpha B is equal to minus alpha A. So instead of alpha B, we can substitute the value minus alpha A. Already there will be a minus in the previous equation. So minus into minus plus. So here we are getting this plus term. So this is A value. Now in this A value, again we are taking alpha A by CAE common. So automatically this value will become 1. Here you can see already you are having a alpha A, so it will become 1. Numerator will become 1. In denominator you are having CAE, which is absent in this second term. So to make it cancel, we get to get the actual value. So you have to multiply the numerator with CAE. So now if you multiply this alpha AE CAE inside the bracket, you will get this answer. So already we know that uh, K value is equal to CBE divided by CAE. It is, I think, in equation 1 or 2. Okay, so now we have here, we have got CAE by CBE. So you can, instead of this value, you can write it as 1 by K, because K is equal to CBE by CAE. So there is a reciprocal of that value is inside this bracket, so you can write it as 1 by K. So this is equation number 9. Yes, you please all note down the equations and the equation number. So K is the equilibrium constant of the reaction. So now you can see, already we know J is equal to L into A. Instead of A, we are substituting this equation 9. You are getting this equation 10. So now you want to know the value of L. So when you compare the equation 5 and 10, so if you compare the equations 5 and 10, you will be getting the L value. So when you compare this equation 5 and 10, the equation 5 and 10 will be having one. So you please go through the equation 5. There you can see you will be having this 1 plus 1 by k will be in common between equation 1, equation 5 and 10. So remaining L value will be, you have to equate this remaining uh, non-identical values in equation 5 and 10. So from that you can get this L value. So you will be getting this L value as such. So L is equal to K1 CAE by RT. So this will be the value which you are getting if you equate to the equation 5 and 10. If you please go through the equation 5, in that equation 5 you will be having J into some value will be there. Along with that, there will be 1 plus 1 by k value will be there. So remaining this value should be equated with the values here I am encircling with this LRT alpha A by CAE. So you will be getting the value for L. So thus the Onsager reciprocal relationship has been proved. Okay, its validity and verified. So thank you.